Hello, and welcome to Sleepy Story Facts. Tonight, you're invited into a quiet sleep story set among the stars. A slow, soothing nighttime story where we explore space in a way that feels safe, gentle, and unhurried. If your day has been loud or heavy, you don't need to carry it any longer. Let your shoulders soften. Let your jaw unclench. Let your breathing find an easy pace, like a slow tide coming in and out. You can listen closely, or you can let the words drift into the background like soft starlight through a window. Either way is perfect. This is a relaxing story made to help you fall asleep and to guide you toward deep sleep without effort. In this peaceful bedtime story, we'll wander through a handful of remarkable facts about the universe, facts that feel like calm little lanterns floating in the dark. Some are serene, like still waters hidden beneath distant ice. Others are powerful, like the quiet engines at the hearts of galaxies. But none of them are here to startle you. They're here to widen the mind just enough, and then gently let it rest. So get comfortable now. Adjust your blanket. Let the room hold you. And as your eyes grow heavier, imagine you're stepping into a slow-moving spacecraft, not rushing anywhere, only gliding, listening to the hush between worlds. And when you're ready, we'll begin. The first thought is a strange one, and yet it can feel oddly comforting. The universe itself is growing, stretching outward so smoothly that, in a sense, it can expand faster than light. That might sound impossible at first. We learn that nothing can travel through space faster than light, and that's true. But space is not a fixed stage. Space is part of the story. It can flex. It can stretch. And when it stretches, it isn't an object breaking a speed limit. It's the distance itself becoming larger. Long ago, in the earliest moments after the Big Bang, the universe went through a period scientists call inflation. In that brief, astonishing instant, space swelled so quickly that regions of the young cosmos were carried apart faster than any beam of light could cross the gap, not because galaxies were racing like rockets, but because the space between them was gently, insistently widening. Even now, far beyond the reach of our best telescopes, the most distant galaxies are being carried away from us in the same quiet manner. The stretch continues. The night keeps opening. And here's the soft, humbling twist. Because of that continuing expansion, there are places whose light will never reach Earth, regions forever beyond our cosmic horizon. They exist peacefully and patiently, yet we can never receive their glow. The universe, in a very real way, is larger than the part we will ever know, and it keeps its distant secrets with a kind of calm grace. As you breathe in and out, you might let that idea settle like a warm, weightless blanket. Not everything needs to be seen. Not everything needs to be solved. Some things can simply be far away and still real. Now, let's drift closer to something brighter. Some stars are so enormous that if one took the place of our sun, it could swallow the inner planets as if they were tiny beads of dust. Try to imagine it slowly, without strain. A star so large that its outer atmosphere would stretch past the paths of Mercury and Venus, past Earth, past Mars, and onward. Not as a sharp edge, but as a vast, glowing presence, like a warm fog lit from within. Among the largest known stars are red supergiants, giant, aging suns that have expanded into enormous, billowing spheres. Their diameters can reach hundreds, even more than 1,000 times that of our sun. Yet despite their size, their outer layers can be surprisingly thin, like a luminous mist. If you could hover near the outer edges, the gravity there might feel gentler than you'd expect. Because the star's mass is spread across such an immense space, these giants don't last long by cosmic standards. They burn their fuel quickly, living for only a few million years, brief lives, compared to our sun's steady, long-burning story. And at the end, they don't fade quietly. They erupt. A supernova is not just an explosion. It's a cosmic turning point, one of the ways the universe rearranges itself, making room for new beginnings. When a massive star dies, it throws its material outward into space. Carbon, oxygen, iron elements built slowly in the star's deep interior over unimaginable spans of time. That cloud of debris expands like a slow-moving, glittering storm, spreading into the dark. Over many ages, it mingles with surrounding gas and dust, cooling, gathering, letting gravity do what gravity always does, pulling, shaping, collecting. And in some regions, that drifting material can become the start of something new, fresh stars forming from old remnants, and planets taking shape in the leftover swirl. In a quiet way, worlds can be born from what a star once was. It's one of the most comforting facts in astronomy. The solid things we know, rock, ocean, mountain, bone, come from ancient stellar lives. We aren't separate from the cosmos. We are part of its recycling, part of its patient craft. The atoms in your body were assembled in processes that began long before Earth existed, in stars that lived and ended and made room for others. If that feels big, let it be big, and then let it become simple again. Breathe in, breathe out. Now we'll drift toward one of the universe's quiet paradoxes, objects known for darkness, that can still send power across incredible distances. Black holes are often described as devourers, places where gravity grows so intense that not even light can escape once it crosses a certain boundary. But around many black holes, especially the supermassive ones at the centers of galaxies, there can be brilliant chaos before the darkness, swirling disks of gas and dust, heated by friction, glowing as they spiral inward. And sometimes, from that bright, spinning region, something astonishing happens. Magnetic fields can twist and organize the infalling material, guiding part of it not into the black hole, but away from it, launched outward in two narrow streams, like twin beams, shooting from the poles at speeds close to light. These jets can stretch for distances that are hard to hold in the mind. Not just across a solar system, not just across a galaxy, but sometimes for millions of light years into intergalactic space. They can shine so strongly that they influence the growth of galaxies themselves, compressing gas in one place to encourage new stars, or sweeping it away in another, slowing star formation like a quiet hand pressing down. It's almost like the universe breathing through a dark center, pulling in and sending out, shaping the vast surroundings with invisible structure and steady force. Even where there is darkness, there can be direction. Even where there is mystery, there can be motion. And now, for a softer kind of wonder, one that feels almost like a dream. On distant ice giants like Neptune and Uranus, scientists think it may literally rain diamonds. Deep in those alien atmospheres, pressure climbs and climbs. Temperatures rise. Molecules that contain carbon, like methane, can be squeezed and shocked so intensely that carbon atoms rearrange into crystal structures. Tiny diamonds may form, then fall downward, sinking through layer after layer like glittering hail in slow motion. Here on Earth, researchers have recreated similar conditions in labs using extremely powerful lasers, compressing materials until microscopic diamond dust appears. It's not just a fantasy. The physics makes sense. And if it can happen there, it might happen on other carbon-rich worlds across the galaxy, quietly making gemstones in places no one will ever visit. Some scientists even imagine larger chunks, diamond icebergs, drifting in the hidden depths, far below the visible clouds. Not to be mined, not to be claimed, just existing, turning storms into silent treasure. And if you let your mind picture it gently, you can almost see that deep blue sky and the slow, sparkling fall, diamonds drifting down like soft snow, vanishing into warmth below. For now, you don't need to hold the image tightly. Let it blur at the edges. Let it become more like a feeling than a picture. Because this is a calming narration, and you can let your thoughts loosen the way a hand relaxes when it no longer has to grip. We'll continue our peaceful journey through the universe in just a moment, with more quiet space facts and more gentle wonders waiting in the dark. Please paste part 2 of your original script when you are ready. We're still drifting gently through the quiet dark of space, as if your thoughts are floating beside you, slow, unforced, and calm. The room around you can stay exactly as it is, warm, still, and safe, while this bedtime story continues like a soft current. And now, one of the universe's long, patient dances. Far beyond our familiar stars, the Andromeda Galaxy is on its way toward the Milky Way. It's more than 2 million light years away, so distant that the mind can't quite hold it. And yet it's there, a faint, misty shape in the sky for those who know where to look. Andromeda is moving closer at roughly 400 kilometers per second, not rushing in a dramatic way, but gliding through the vastness, guided by gravity's steady pull. In about 4 billion years, the two galaxies will meet. It helps to imagine this not as a crash, not as broken glass and impact, but as two slow clouds passing through one another. Stars are separated by enormous distances. In most cases, they won't collide directly. Instead, gravity will do what it always does, gently, but irresistibly reshaping the larger pattern. The Milky Way and Andromeda will begin to stretch each other into long, curved streams. Their spiral arms may distort into sweeping arcs, and faint, tidal tails of stars could unfurl into the surrounding dark like ribbons in slow motion. Over time, the two great systems will blend into a single, larger galaxy, one calm, grand structure formed from two older ones. Some people call this future galaxy Milkdromeda, a playful name for an event that will feel almost like cosmic weather. Not a storm you fear, but a slow change of seasons across billions of years. If anyone could watch the sky during that era, it would be breathtaking. Andromeda would no longer be a distant smudge. It would spread across the heavens as a luminous sweep, bright and wide, filling the night with layered light, like a second river of stars pouring over the first. The familiar shapes of constellations would dissolve. The sky would become a moving mural, and our sun, if it's still shining then, might drift into a different orbit, carried by the new galaxy's reshaped gravity. Not lost, not thrown into chaos, just relocated, like a leaf carried to another quiet bend in a stream. Galaxy mergers, it turns out, are common. In fact, the Milky Way has grown this way before, slowly absorbing smaller galaxies over its long history. So this future meeting isn't an ending. It's another chapter in the way the universe builds patiently, gradually, and without hurry. And now, as this relaxing story continues, let your attention drift closer to something smaller than a galaxy, yet so intense it feels almost unreal. When a massive star reaches the end of its life, it can collapse into an object called a neutron star. Picture something only about 20 kilometers across, small enough to fit within a city, yet containing more mass than our sun. Matter there is compressed to an extraordinary density, as if the star's heart has been pressed into a single heavy jewel. Some neutron stars spin incredibly fast. These are often called pulsars. They can rotate dozens, even hundreds of times per second, turning with such precision that their rhythm can rival our finest clocks. That speed, paired with immense gravity, affects the space around them in subtle, powerful ways. Space-time itself becomes slightly distorted, like fabric pulled tight and twisted. Pulsars also carry strong magnetic fields. From their magnetic poles, they can send out beams of radiation. As they rotate, those beams sweep across space like the steady turning of a lighthouse lamp. And if Earth happens to be in the path of one of those beams, we detect a repeating pulse, a calm, regular signal arriving from deep space, again and again. Astronomers use these cosmic beacons to map parts of our galaxy and to test the rules of gravity under extreme conditions. They're reminders that the universe has its own kind of timekeeping, quiet metronomes ticking far beyond our night. If you imagine standing near one, just as a thought experiment, safe and distant, it would feel like being beside a mountain that spins impossibly fast, a small thing in size, and yet unimaginably powerful in presence. From these bright, rhythmic objects, we can drift toward something almost the opposite: galaxies that barely shine at all. Not every galaxy is full of bright stars. Some appear to contain a great deal of gas, but very little starlight, so little that they can be hard to notice, even with powerful telescopes. People sometimes refer to these as dark galaxies because they're nearly invisible in ordinary light. We find them in quieter ways, by listening for their gas with radio telescopes, or by watching how their gravity bends the light of objects behind them, like a gentle lens. In a universe where so much is discovered by seeing, these hidden galaxies teach a softer lesson. Sometimes you learn by noticing what's missing, or by sensing the shape of an unseen presence. Scientists think some dark galaxies might be leftovers from early cosmic times, systems that never fully lit up with star formation. As if they paused before the fireworks began, studying them may help us understand why some galaxies flourish into brilliant spirals, while others remain dim and quiet. They may also offer clues about dark matter, the invisible scaffolding that seems to shape much of the universe's large-scale structure. If you could float near one, there might be no glowing lanes of stars, no bright core to guide your eyes, just a vast, silent gathering of gas and dust. A city with most of its lamps never turned on. And now, staying with that theme of hidden worlds, let's move to planets that travel without any star at all. Most planets belong to a solar system, circling a sun the way thoughts circle a familiar idea. But some planets are cast free. Through gravitational encounters, close passes with other planets or stars, worlds can be nudged out of their birth systems and sent wandering alone. These are rogue planets, drifting through interstellar space with no sunrise and no sunset. Their skies would be perpetual night. Their only warmth might come from leftover heat from their formation, slowly leaking out over ages, or from gentle radioactive decay deep inside their rocky interiors. Even without a star, some may hold onto thick atmospheres. Some might shelter subsurface oceans beneath heavy ice, insulated like a secret, kept warm under a blanket. And it's possible, some astronomers suspect, there could be more rogue planets in the Milky Way than there are stars. Hidden worlds, quiet travelers, whole planets passing through the galaxy like silent ships. They're difficult to find, but sometimes we catch them briefly when they cross in front of a distant star, dimming its light for a moment. A soft blink in the sky that hints at a dark object drifting between us and the far distance. There's something haunting about the idea. Yes, but also strangely peaceful. A world with no dawn still has motion. A place with no sunlight may still have warmth somewhere deep within. Even in endless night, there can be pockets of life-friendly quiet, sealed away and steady. Now, let's return closer to home, to a star we think we know well, and one of its gentlest mysteries. The sun's outer atmosphere is hotter than its surface. It sounds backwards, like a riddle. The sun's visible surface, the layer we see, has a temperature around 55°C, yet above it, the thin outer atmosphere, called the corona, reaches temperatures of more than 1,000,000 degrees. Scientists are still working to fully explain how this happens. One strong idea is that the sun's magnetic fields become tangled and stressed, then suddenly rearrange, snapping and releasing energy in many small events, like quiet sparks that collectively heat the corona. Waves moving through the sun's plasma may also carry energy upward, warming that outer region in a way we're still learning to describe. The corona stretches far into space, shaping the solar wind, the stream of particles that flows outward through the solar system. And sometimes, during a total solar eclipse, the moon blocks the bright face of the sun and reveals the corona as a pale halo, ghostly and delicate, like white silk around a hidden lamp. This superheated atmosphere matters to us in practical ways too. It plays a role in space weather, which can affect satellites and communication systems on Earth. Understanding the corona isn't just curiosity. It's part of learning how our star breathes and how that breath touches our world. And before we move on, here's one more gentle rhythm to listen for in the sky. Some stars flicker and change brightness over time. These are called variable stars. Their changes can happen for different reasons, and each reason tells a quiet story about the star's life. Some variable stars expand and contract, their outer layers pulsing like a slow exhale and inhale. Others have spots and flares, stellar, whether that causes their light to rise and fall. The way our own sun's activity can vary. And in some systems, two stars orbit each other so closely that one regularly passes in front of the other, creating a repeating dimming, an eclipsing binary, like a gentle curtain being drawn and lifted again. Certain kinds of variables are so regular and reliable that astronomers use them as distance markers, helping measure how far away other galaxies are. These stars become soft tools for mapping the universe, turning flickers into measurements and rhythm into knowledge. To the early skywatchers, a changing star could feel unsettling, like the heavens were shifting. But now, we understand it as something natural and calm. A star simply showing another side of its existence. And if you listen to those distant changes with your imagination, it can feel like the cosmos has a heartbeat, slow, steady, and endlessly patient. A rhythm that doesn't demand your attention, only offers it. We're still in the same gentle nighttime story, drifting from wonder to wonder at a pace that doesn't ask anything of you. Imagine the lights are low, your breathing is slow, and the universe is simply unfolding above you like a quiet ceiling of velvet. Tonight's relaxing story keeps moving through space facts that feel enormous, but are told softly, the way you might speak in a dark room when someone is already half asleep. And now, let's float toward a giant planet where weather never really ends. On Jupiter, storms can grow so large they make Earth seem small by comparison. The most famous is the Great Red Spot, a vast swirling storm that has been observed for centuries, an ancient, rotating oval of cloud, tinted in rusty reds and warm browns. It's an anticyclone, meaning it spins in the opposite direction of many storms we're used to thinking about on Earth. For a long time, this storm has been so wide that multiple Earths could fit inside it, and within it, winds race at tremendous speeds, fast enough to remind you that Jupiter is not a quiet place, even if you're viewing it from far away, safely wrapped in the calm of your bed. That reddish color likely comes from chemistry high in Jupiter's atmosphere, sunlight interacting with complex molecules, changing them subtly over time, like pigments deepening in slow motion. Jupiter's rapid rotation helps organize its clouds into bands that wrap around the planet, and heat rising from inside the gas giant keeps the atmosphere active, energized, and constantly reshaping itself. On Earth, storms weaken when they cross land or run out of warm ocean to feed them. Jupiter has no solid surface to interrupt the flow. No forests, no mountains, only layers of gas and cloud, one beneath another, like an endless sky. And so some Jovian storms can persist for decades, even centuries. In recent years, scientists have noticed that the Great Red Spot has been shrinking. It's still immense, still unmistakable, but it seems to be slowly changing shape, as if even the oldest storm is, at last, learning how to fade. And yet, Jupiter keeps making new tempests, other swirling ovals rising and dissolving in the bands, reminding us that some worlds have weather that feels like a permanent, living feature. Stay with that feeling for a moment, a storm that lasts longer than human history, turning and turning, while you, here and now, can simply rest. From Jupiter's restless clouds, we can drift back to one of the densest ideas in all of astronomy, an idea so extreme it almost turns into a lullaby for the mind, because it's too strange to hold tightly. A neutron star is what can remain after a massive star collapses. Imagine an object only about 20 kilometers across, yet holding more mass than the sun. Matter there is packed so tightly that atoms can't keep their usual shape under such crushing pressure. Electrons and protons combine, forming a sea of neutrons, dense beyond ordinary intuition. This leads to one of those famous, startling comparisons. If you could somehow collect a single spoonful of neutron star material, it would weigh billions of tons on Earth. It's the kind of fact that doesn't need to be imagined too vividly. You can let it remain a gentle thought, like a heavy stone resting deep underwater. The point isn't to stress the mind, it's to feel, briefly, the scale of what nature can do. The gravity at a neutron star's surface is so intense that it can noticeably bend light. Time itself behaves a little differently so close to such an object, in the way strong gravity can subtly slow the flow of time compared to faraway regions. Many neutron stars spin rapidly, some rotating dozens or hundreds of times per second. And as we mentioned earlier in this bedtime story, some of them send out beams of radiation that sweep through space like a lighthouse beam. When that beam crosses Earth, we detect a pulse, steady, calm, repeating. If a fragment of neutron star density could be brought to Earth, which, realistically, it can't, it wouldn't sit safely in a container. Our planet's crust could not support that kind of compact mass. But you don't need to chase the dramatic edge of the idea. You can simply take the softer truth. The universe makes objects that stretch the rules of what feels possible, and it does so quietly, without needing our approval. Now, let's move to something far more delicate to picture, something you can almost see with your eyes, even from Earth, with a small telescope and a patient evening. Saturn's rings, those pale, glowing arcs, are not permanent. They look timeless, like a symbol that has always belonged to Saturn. But the rings are made mostly of water ice, mixed with dust and rocky fragments, and they're slowly changing. Tiny impacts from micrometeoroids darken and disturb the particles. Saturn's gravity tugs on the ring material, and bit by bit, some of that icy debris spirals inward. Scientists call part of this process ring rain, because particles from the rings fall down into Saturn's upper atmosphere, like a very thin, invisible drizzle of ice and dust. Over a long enough time, the rings can thin out and fade. Estimates vary, but some suggest Saturn's rings could largely disappear within about 100 million years. Just a blink on cosmic timescales, though still far longer than any human lifetime. Spacecraft observations, including those from Cassini, also suggest the rings may be younger than Saturn itself, possibly formed when a moon or comet was broken apart and spread into a wide, shining disk. For now, they remain one of the most beautiful sights in the solar system. Quiet, luminous bands reflecting sunlight in soft silver tones. And their slow disappearance carries a gentle lesson that fits well in a nighttime story. Even the loveliest structures are not frozen forever. Change is part of the calm design. From the slow fading of rings, we can drift to an ending that happens in the opposite way, sudden, swift, and immense, though we'll hold it gently, without harshness. When a very massive star runs out of the fuel that supports it, gravity finally wins. The core collapses with astonishing speed, shrinking dramatically in less than a second. That rapid collapse can create a powerful shock that rebounds outward, blasting the outer layers into space. A supernova can briefly shine with the light of an entire galaxy, not because it wants to be seen, but because physics allows that much energy to be released in a single, short event. And when it's over, the core may become a neutron star, or, if it's massive enough, a black hole. It's tempting to describe such an event as violent, and in a technical sense, it is. But from far away, across the quiet distances, it's also part of the universe's steady cycle: collapse, explosion, dispersal. And then, over ages, new clouds gathering to form new stars and planets. Those explosions scatter heavy elements outward, enriching the galaxy with the ingredients that later become worlds. In that way, even a star's sudden ending becomes a kind of gift, matter released, redistributed, made available for new stories. Now, let's soften even further and listen for a whisper that fills all of space. No matter where you point a telescope, no matter how empty the region seems, there is a faint background glow. It's not visible to your eyes, but instruments can detect it. The cosmic microwave background, often described as the afterglow of the Big Bang. This delicate radiation is like an ancient echo, stretched into microwave wavelengths as the universe expanded. It comes to us from a time when the cosmos was only about 380,000 years old, when it cooled enough for atoms to form, allowing light to travel freely for the first time. In that faint glow, there are tiny variations, subtle differences in temperature and density, that became the seeds of everything larger. Galaxies, clusters, vast structures of matter. Scientists map this background with extraordinary care because it helps reveal the universe's age, its composition, and how it has grown. But in the calm tone of this sleep story, you don't need the measurements. You can just keep the feeling. Space is not truly empty. It holds a quiet memory of its beginning, a soft, universal whisper still traveling after more than 13 billion years. And now, to finish this part of our bedtime story, let's come home to something close and familiar. The moon. The moon is slowly drifting away from Earth. Each year, it moves about 4 centimeters farther out. It's a change too small to notice in daily life, yet it's steady and it's real. The reason is tidal interaction. The moon's gravity pulls on Earth's oceans, raising bulges. As Earth rotates, those bulges are carried slightly ahead of the moon, and their gravitational pull transfers a tiny bit of energy, nudging the moon outward while gradually slowing Earth's rotation. Long ago, the moon was closer, days were shorter, and evidence for that shows up in surprising places, like ancient coral growth patterns, which can record how many days were in a year, revealing that hundreds of millions of years ago, more days fit into the same orbit around the sun, because each day was a little briefer. Over immense timescales, this widening distance will change how eclipses look from Earth. Total solar eclipses, perfectly matched in apparent size, are a temporary gift of geometry. In the far future, the moon will appear smaller in the sky, and total eclipses will eventually become rare, and then impossible. But for now, the moon still keeps its gentle rhythm above us, and its gradual journey outward is like a quiet reminder that even the closest relationships in the cosmos are always slowly evolving. In this calming narration, you can let that thought settle peacefully. Change doesn't always arrive as a disruption. Sometimes it arrives as a whisper, 4 centimeters at a time, soft enough that you can keep resting while the universe continues to move. We're still traveling gently through this calming space bedtime story, as if we're floating in a quiet observatory where nothing is urgent and everything moves at a soothing pace. The night around you can remain soft and still, and the universe can feel like a distant, peaceful ocean. In this relaxing story, the next fact is about something famously dark, yet strangely elegant in the way it shapes the space around it. Some black holes spin so quickly that their rotation comes close to the ultimate speed limit, the speed of light. A black hole doesn't just sit there like a motionless pit. Many of them rotate, carrying angular momentum from the star that collapsed to form them. And over time, they can gain even more spin as they pull in gas, dust, or even other objects, adding new motion to the whirl. When a black hole spins fast, it doesn't only affect nearby matter, it affects space-time itself. There's an effect called frame dragging, where the rotation of a massive object tugs on the fabric of space-time, pulling it around as it turns, like a slow whirlpool in a river, not just moving water, but subtly shaping the flow nearby. In the region close to a rapidly rotating black hole, it becomes difficult, almost impossible, for anything to remain truly still. Motion is encouraged in the same direction as the spin, as if the universe itself is being gently persuaded to follow along. This spin also changes how matter behaves in the glowing disk around a black hole, the accretion disk, where gas heats up as it spirals inward. A faster spin can influence how close that orbiting material can safely circle before plunging in. It can also affect how easily the system launches powerful jets, those narrow streams that shoot outward along the poles, sending energy into the surrounding galaxy. Measuring a black hole spin is not simple. Astronomers infer it by studying light from the hot material nearby, looking for subtle signatures in the way that light is shaped by extreme gravity and rapid motion. It's delicate work, like learning about a dancer in the dark by watching the motion of the curtain. And there's another quiet detail. When a black hole rotates, the size and shape of its point of no return, the event horizon, can change compared to a non-rotating black hole of the same mass. Rotation alters the geometry, as if the darkness has a slightly different contour when it's in motion. You don't need to picture it sharply. You can let it remain a soft idea, a dark object spinning so quickly that it gently drags space itself along for the turn. Now, from a small region of intense gravity, let's drift outward to something vast and glowing. One of the largest stars we know, there is a red supergiant called Scuti, often mentioned among the biggest known stars by size. If it were placed where our sun is, its outer layers could stretch beyond the orbit of Jupiter. Just imagining that can feel like trying to fit a mountain into a teacup. Your mind might smile and let it go. Its diameter is estimated to be well over 1,000 times that of the sun, and its volume is so enormous that millions of Earths could fit inside, like tiny marbles floating in a warm, luminous haze. And yet, for all that size, the star's outer atmosphere is not a hard surface. It's diffuse, more like a glowing veil than a solid boundary. The edge is a region, not a wall, a faint, expanded envelope of gas, shining softly, drifting outward. Stars like this live fast by cosmic standards. They burn through their fuel quickly, spending only a few million years in this inflated phase before they collapse and explode as supernovae. They're rare and they're temporary, and that's part of what makes them feel so dreamlike, enormous lanterns in space that do not stay lit forever. If you could watch one from nearby, at a safe, impossible distance, it might feel like looking at a living landscape of fire, so wide it could swallow familiar worlds without noticing. But you're here, safe in the quiet of your room, only borrowing the image for a moment before letting it fade. Next, we'll return to the earliest light of all, but in a way that feels almost like listening. The universe carries a faint, ancient glow. The cosmic microwave background, a leftover signal from when the cosmos was only about 380,000 years old. It isn't sound. Space is far too empty for sound to travel in the usual way. But the pattern of tiny fluctuations in this background light can be translated into audio. Scientists can take the data, those slight differences in temperature and density, and turn them into tones. It becomes something you can hear, not as a literal recording, but as a gentle sonification. Information transformed into sound. Listening to it is like listening to the universe remembering. Those tiny ripples were the early unevenness that later grew into everything larger galaxies gathering, stars igniting, planets forming. The pattern is remarkably consistent across the sky, and yet filled with subtle variations that help scientists understand what the universe is made of, how old it is, and how it may evolve. In the tone of a nighttime story, the feeling is simple and soothing. Even the emptiest looking space is not truly blank. It holds a soft trace of beginnings, light that has traveled for more than 13 billion years, still arriving, still whispering. Now let's float closer to a neighboring world, rust-colored, quiet, and full of frozen history. Mars is home to the tallest volcano in the solar system, Olympus Mons. It rises nearly 22 kilometers above the Martian surface, about 2.5 times the height of Mount Everest. But what's even more striking is its width. Olympus Mons stretches roughly 600 kilometers across, so broad that it would cover an enormous portion of a continent on Earth. It's a shield volcano built by lava that flowed slowly and steadily over very long periods. On Mars, the conditions allowed it to grow far larger than Earth's volcanoes. Mars has lower gravity, which makes it easier for huge structures to build upward. And Mars doesn't have active plate tectonics in the way Earth does, so the ground beneath the volcano didn't shift and carry it away from its magma source. It could keep building in the same place, layer by layer, as if time itself was patiently stacking stone. If you stood at the base of Olympus Mons, the summit would be so far away that the curve of the planet would hide it. You wouldn't see the top like a pointed peak. You'd feel the slope as a gentle rise, like standing on the lower edge of a sleeping giant. Though it's considered dormant, some of its features appear geologically young, suggesting Mars has not completely finished with its volcanic stories. Not today, not tomorrow, but somewhere in the far distance of time, the planet may still have warmth to offer. And now, let's turn to visitors, icy travelers that sometimes arrive from places we can barely name. Most comets we observe come from the far edges of our own solar system, the Kuiper Belt, beyond Neptune, or the distant Oort cloud, a vast halo of icy bodies surrounding the sun's domain. But every so often, something different appears, an object passing through too fast, on a path that isn't bound to the sun. These are interstellar visitors, bodies that likely formed around other stars and were flung outward long ago by gravitational interactions. Objects like Oumuamua and Comet 2 I/Borisov reminded us that space is not divided into neat neighborhoods. Material can drift between star systems for millions of years, crossing the darkness like a quiet message in a bottle. When such an object passes through our solar system, we have only a brief chance to study it, weeks or months of visibility, before it continues onward, never to return. Unlike many comets whose orbits we can predict again and again, these travelers are one-time guests. And that feels fitting for a sleep story. A slow, temporary arrival, a soft passing, then a fade back into the deep. Now we'll return gently to the moon, because there's a phrase we often use that isn't quite accurate. People sometimes say the dark side of the moon, but it isn't truly dark in the sense of never seeing sunlight. Every part of the moon experiences day and night during its month-long orbit. The more accurate idea is the far side, the side that always faces away from Earth, because the moon is tidally locked, turning in such a way that it keeps the same face toward us for most of human history. That far side remained unseen, hidden simply because we couldn't travel above the moon and look back. It wasn't photographed until 1959, when the Soviet spacecraft Luna 3 sent back the first images, and the far side looks different. It has fewer of the dark, smooth plains we call Maria, and many more craters, giving it a rugged, battered appearance, as if it held onto a different version of lunar history. So it's dark, only in the sense that it was unknown to us for a long time. A reminder that language can shape the way we imagine space, sometimes making a mystery feel more dramatic than it needs to be. In reality, both sides of the moon share the same rhythms: bright sunlight, long shadows, deep cold, and quiet nights. And for our final gentle curiosity in this part, we'll visit a region of our galaxy that offers something unexpectedly familiar, an echo of taste and scent, carried by chemistry. Near the center of the Milky Way, in a large cloud of gas and dust called Sagittarius B12, astronomers have detected a molecule known as ethyl formate. On Earth, this compound is associated with a smell like rum and a flavor sometimes described as raspberries. Of course, that doesn't mean the Milky Way is a place you'd want to breathe in. The reality of such clouds is harsh and toxic, full of radiation and chemicals in conditions nothing like a kitchen or a garden. But the discovery is still charming in a quiet way, because it shows that some of the building blocks related to familiar aromas and flavors can form naturally in space. Molecules assemble on the surfaces of tiny dust grains, then drift free when warmed. Tiny chemistry experiments happening in the dark, far from any planet. It's a soft reminder that the universe isn't only made of distant abstractions. It's made of the same kinds of atoms and bonds we know here, rearranged into new forms, drifting between stars. And as you rest with that thought, you can let your mind loosen even more. Because in a bedtime story like this, curiosity doesn't need effort. It can be gentle. It can be slow. It can fade into sleep. We're still floating through this nighttime story together, moving at a pace that feels unhurried and safe. If your thoughts have started to soften around the edges, that's perfect. You don't need to concentrate. Just let the words pass by like faint constellations there, and then gone. In this relaxing story, we're going to visit a kind of milestone that feels both scientific and quietly emotional. The moment a human-made object leaves the sun's neighborhood and begins the long glide between the stars. 2 spacecraft have done exactly that. Voyager 1 and Voyager 2, launched by NASA in 1977, have traveled so far that they crossed a boundary called the heliopause, the distant region where the solar wind from our sun fades and yields to the interstellar medium beyond. Voyager 1 reached that boundary in 2012. Voyager 2 followed in 2018. It's hard to picture how far away that is, so you don't need to try too hard. Just imagine distance that turns into patience. Imagine a small, steady machine moving outward year after year, while Earth spins through seasons and generations. Out there, the influence of other stars begins to mingle with our own. The environment changes, particle densities, magnetic fields, the subtle texture of space itself. And remarkably, those aging spacecraft have continued to send back measurements, giving humanity a first, direct taste of what the space between star systems is like. Each Voyager also carries something tender and symbolic, a golden record filled with sounds, images, and greetings from Earth, a carefully chosen message, like a bottle set afloat on a cosmic ocean. It wasn't sent with any certainty that it would be found. It was sent as a quiet gesture of hope and curiosity. Their power will not last forever. Their instruments will eventually fall silent, but the spacecraft themselves will keep traveling, coasting through the galaxy, for an unimaginably long time, long after the details of our present day have changed. If you let that thought land gently, it can feel comforting, something small and human-made moving through the dark, not in fear, just in motion. Now, as we continue this bedtime story, we'll drift to another kind of hidden treasure, quiet rocks in space that carry the heavy history of early planets. Most asteroids are stony or rich in carbon, dark and ancient. But a rarer group is made largely of metal, iron, and nickel, and sometimes traces of valuable elements like platinum. A famous example is the asteroid 16 Psyche, which many scientists think could be the exposed core of a protoplanet that never fully became a world. Long ago, collisions and chaos in the early solar system may have stripped away its outer layers, leaving behind something like a planetary heart, metallic, dense, and strangely pure. People sometimes mention its value in money because the metal content is so large that, in theory, it could exceed all wealth on Earth. But that kind of number is more dream than plan. Mining an asteroid and transporting materials across space is far beyond simple economics. The real beauty is what these objects can teach us. Studying metallic asteroids helps scientists understand how planets differentiate, how heavy materials sink inward to form cores, while lighter materials rise to form crusts. These space rocks are like fossils from the solar system's earliest workshop. And someday, far in the future, they may even become useful resources for building in space, so that we don't always have to lift every material from Earth's deep gravity well. But that's a story for another night. For now, we'll move to a planet with a timekeeping puzzle, one that feels like the universe playing softly with definitions. On Venus, a single day lasts longer than a year. Venus rotates very slowly. One full spin on its axis takes about 243 Earth days. But Venus orbits the Sun in about 225 Earth days. So by that simple comparison, the planet completes its year before it finishes one rotation. And there's an extra twist. Venus spins in the opposite direction compared to most planets in the solar system. If you could stand above its cloud tops and watch the sky, the sun would appear to rise in the west and set in the east. Why is Venus like this? Scientists still debate the details. It could be the result of ancient collisions long ago, or gradual interactions, tides and torques, between Venus, the Sun, and Venus's thick atmosphere over vast stretches of time. Venus is wrapped in dense carbon dioxide clouds and has extreme surface temperatures, creating an environment that's harsh and pressurized. Nothing like a gentle Earth evening, and yet, beneath the clouds, Venus has mountains and vast volcanic plains, signs of a complex geological history that we're still learning to read. Even an inhospitable world can be full of clues, like a sealed book waiting for the right light. Now, let's cool the imagination way down to a place so cold it feels like silence made physical. There is a nebula called the Boomerang Nebula, about 5,000 light years away, known for being the coldest natural place we've measured in the universe. Its temperature drops to about 1 degree above absolute zero, colder even than the faint background warmth left over from the Big Bang. It becomes, in a sense, colder than empty space, because space is never perfectly empty and never perfectly cold. This extreme chill happens because gas from a dying star is expanding outward very rapidly. When a gas expands quickly, it cools, like breath fogging in winter air. But on a cosmic scale so large, it becomes almost poetic. The Boomerang Nebula has an eerie, hourglass-like shape. In visible light, it can look faint and ghostly, but in radio wavelengths, it becomes bright, revealing more of its structure. It's like a natural freezer in the sky, holding its material in a deep cold that Earth can barely imitate. Over time, this won't last. The central star will evolve, heating and changing, and the nebula will disperse. But for now, it remains a quiet record holder, proof that even in a universe filled with fire and fusion, there are pockets of astonishing cold. And now, with the calm tone still intact, we'll touch on something dramatic in nature, but we'll handle it gently, the way a sleep story does, as distant, slow, and safely observed. Sometimes a star wanders too close to a supermassive black hole. When it does, the black hole's gravity doesn't simply pull the star in whole. The difference in gravitational pull from one side of the star to the other becomes enormous. This creates tidal forces that can stretch the star apart, pulling it into a long stream of glowing gas. Astronomers call this a tidal disruption event. Part of that stellar material spirals inward, forming or feeding an accretion disk. As the gas falls closer, it heats up and emits intense light, sometimes bright enough to outshine the galaxy for a while, visible across great distances. The rest of the star's material can be flung outward, thrown back into space at tremendous speeds, like a bright ribbon snapping away. These events are rare in any single galaxy, but when they happen, they offer scientists a chance to observe black holes indirectly, to watch how they feed, how they shape their surroundings, how gravity behaves at its most extreme. In the safe distance of this bedtime story, the feeling isn't fear. It's awe, quiet and far away. A reminder that even bright, massive stars can be delicate when placed too close to the deepest wells of gravity. And now, to end this part on a lighter, almost playful note, let's return to Saturn, not its rings this time, but a simple, surprising comparison. Saturn is so low in average density that if you could place it in an ocean large enough, it would float. Its average density is less than water. That's because Saturn is made mostly of hydrogen and helium, with only a small core of heavier elements. It's a giant ball of gas, more like a world-sized cloud than a rocky sphere. Of course, no ocean could truly hold a planet. It's only a thought experiment, but it's a gentle one, an easy mental image that shows how different Saturn is from Earth. And there's another quiet truth tucked inside that idea. Saturn has no solid surface you could stand on. If you descended into its atmosphere, you'd pass through layers of cloud and haze as pressure increased and increased until the conditions became crushing and the concept of standing stopped making sense. Lightness and immensity, beauty and strangeness, Saturn holds them together like a calm paradox in the night sky. And as you rest here, listening to this calming narration, you can let these facts blur into one soft drift, like a peaceful night ocean under starlight, carrying you closer and closer to sleep. We're still moving through this gentle bedtime story at the same quiet pace, as if the universe is turning its pages for you slowly, softly, while you rest. If you notice your eyelids growing heavier, you can let them. This is a sleep story, and it's meant to feel easy. Let's begin this part with a small surprise about warmth and distance. The hottest planet in our solar system is not the one closest to the sun. Mercury is nearest to the sun, yes, but Mercury has almost no atmosphere to hold onto heat. Venus, on the other hand, wears a thick blanket of air, mostly carbon dioxide, and that changes everything. Venus's average surface temperature is around 465 C. Hot enough to melt some metals, hot enough to overwhelm most machines we've ever sent there. This heat comes from a runaway greenhouse effect. Sunlight arrives, warming the surface, and the thick atmosphere traps that heat, making it difficult for warmth to escape back into space. Venus also has bright clouds of sulfuric acid that reflect a portion of sunlight, giving the planet its pale glow. But those same clouds sit above an atmosphere that still holds heat close, sealing it in. It becomes a world of relentless temperature, where a spacecraft can survive only a short time on the ground before the environment takes it. Venus can feel like a cautionary tale, a reminder of how powerfully greenhouse gases can reshape a planet's destiny. And yet, beneath its hostile skies, the landscape is real and varied. Wide plains, volcanic regions, and mountain ranges, quiet evidence that Venus has a long geological story that scientists are still trying to understand. Now, from that heat, let's drift outward to places that seem like they should be cold and still, and yet remain surprisingly alive. Some moons are geologically active. It's easy to imagine moons as frozen, silent spheres, old and unmoving. But the solar system is more dynamic than that calm picture suggests. Take Io, one of Jupiter's moons. Io is the most volcanically active body we know, dotted with hundreds of volcanoes. Its heat doesn't come mainly from sunlight. It comes from tidal forces, Jupiter's gravity squeezing and flexing the moon as it orbits, warming its interior the way bending a material over and over can create heat. Then there's Enceladus, a small moon of Saturn that seems, at first glance, like an icy marble. And yet it sprays jets, geysers of water vapor, and tiny ice grains out into space. Those gentle plumes help feed material into Saturn's ring system, like a quiet fountain running in the cold. And far away, Triton, Neptune's moon, shows signs of cryovolcanism, volcano-like activity, where the lava can be water, ammonia, or methane, erupting in strange, cold chemistry rather than molten rock. When we find moons like these, the implication is soft but exciting. Internal heat exists even far from the sun. And where there's heat, there can sometimes be liquid water under ice, subsurface oceans kept warm and hidden. It's one of the reasons moons are such intriguing places in space science. They hint that habitable environments might exist in unexpected corners of the solar system. Now, let's bring the scale back closer to home with a simple distance that still surprises many people. The space between Earth and the Moon is wider than it looks. On average, the Moon is about 384,400 kilometers away. And here's a calm little thought experiment. That gap is large enough to fit all the other planets: Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, lined up side by side, with a bit of room left over. It's a gentle reminder that space is roomy, even right here in our cosmic backyard. The Moon can look close in the night sky, large and familiar, but its apparent size is partly a trick of perspective. In reality, the distance is vast enough to hold a procession of worlds. And when you think about the spacecraft that have traveled to the Moon, every mission crossing that wide, quiet gap, it can make those journeys feel even more impressive, not because of drama, but because of distance, precision, and patience. Now, let's widen our view again, past the bright disk of the Milky Way, to something we can't see at all. The Milky Way is surrounded by a halo of invisible matter. Our galaxy doesn't end where the stars thin out. Beyond the visible spiral disk, scientists believe there is a huge halo of dark matter mass that does not emit light or absorb it in the usual way, making it effectively invisible. And yet it has gravity. It pulls. It shapes. We infer its presence by watching motion, how stars orbit in the outskirts, how gas clouds behave, how galaxies hold together when based on visible matter alone. They should be flying apart. The dark matter halo acts like an unseen scaffold, giving galaxies extra gravitational glue. Some estimates suggest that this halo contains far more mass than all the Milky Way's stars combined, which is a strangely soothing idea for a sleep story. Most of what holds our galaxy together is something we cannot see: quiet support, invisible structure. Now, let's touch an idea that links gravity to something even more intimate: time. Time moves differently in stronger gravity. Einstein's general theory of relativity tells us that gravity and time are connected. Where gravity is stronger, time passes a little more slowly compared to places where gravity is weaker. On Earth, the difference is tiny, but it's real, measurable, and confirmed. Atomic clocks flown on airplanes and carried by satellites have demonstrated this effect. Time ticks at slightly different rates depending on speed and gravity. It's not only an idea for science fiction. It's part of how the universe actually behaves. Near extremely massive objects like neutron stars or black holes, the effect becomes much more dramatic. In theory, someone orbiting close to a black hole could experience hours, while far away, much more time passes. You don't need to picture that intensely. Just let it be an elegant thought. Time is not a rigid river. It has currents. It responds to mass. And now, for the final quiet wonder in this part: black holes that don't sit at the center of a galaxy like a throne, but wander. The universe may be full of roaming black holes. We often imagine supermassive black holes anchored in galactic centers, and many are. But smaller black holes, formed from collapsing stars, can drift through the galaxy on their own. They're difficult to detect because they don't glow unless they interact with something nearby. Some may have been kicked outward by gravitational encounters. like billiard balls, exchanging momentum in slow motion. Others could be flung away during black hole mergers, recoiling as gravitational waves carry energy and momentum off into space. Astronomers have begun to identify candidates by watching for gravitational lensing. When an unseen object passes in front of a distant star, and its gravity bends the starlight, causing a subtle brightening or shift, it's a quiet signature, a gentle clue. These wandering black holes are like cosmic ghosts, traveling silently through the Milky Way. Not hunting, not chasing, simply moving along their paths, each one a place where gravity becomes deep enough that space and time fold into a shape we're still learning to describe. And as you rest here, listening to this calming narration, you can let that thought become softer and softer until it's just the feeling of distance and quiet and slow drifting, guiding you towards sleep. We're still in the same soothing sleep story, moving gently from one quiet wonder to the next. Imagine it's late at night in our little story world, your room calm, your breathing slow, while the universe continues its patient motions far beyond the window. In this part, we'll linger on stars again, but with a twist that feels like hearing a familiar song played in a new key. Some stars can be powered by helium, not hydrogen. Most stars, including our sun, spend the majority of their lives fusing hydrogen into helium in their cores. It's the steady, long-burning process that makes starlight feel dependable. But when the hydrogen fuel in the core runs low, a star changes. In more massive stars, the core can grow hot and dense enough to ignite helium fusion. When helium begins to fuse, it can form heavier elements, especially carbon and oxygen. It's a later chapter in a star's life, a warmer, more intense kind of burning that doesn't last as long as the quiet hydrogen phase. And in rarer situations, a star can lose its outer hydrogen layers early, sometimes because it has a close companion star. In a binary system, one star can strip material away from the other through mass transfer, peeling off the outer envelope and revealing deeper layers. The star that remains can be helium-rich, shining hotter and bluer than a typical star of similar mass, living a shorter, brighter life. These helium stars are like glimpses behind the curtain of stellar evolution. When astronomers study them, they're not only looking at an oddity, they're learning about the pathways that can lead toward supernovae, and about how stars age when their usual fuel story changes. Now, let's stay with the theme of unexpected places and visit one of the strangest: planets orbiting a pulsar. A pulsar is a neutron star that spins and sends beams of radiation sweeping through space. It's already an extreme object, dense, fast, precise. And yet, in 1992, astronomers discovered something that surprised the world: planets orbiting a pulsar. These were the first confirmed exoplanets ever found. The environment around a pulsar is not gentle in the way Earth is gentle. Radiation can be intense. Conditions can be harsh. If life exists there, it would not be life as we usually imagine it. But the mere existence of pulsar planets tells us something beautifully wide. Planet formation, or planet survival, can happen in places that feel almost impossible. Some pulsar planets might be leftovers, remnants of a system that changed dramatically when the pulsar was born. Others may have formed from material that fell back and gathered into a disk after the supernova, gradually assembling into worlds over time. The details can vary, but the message stays calm and clear. Nature is creative, even in extreme corners. Astronomers can detect these planets because pulsars keep time so precisely. Their pulses arrive with extraordinary regularity. And when a planet orbits a pulsar, it tugs very slightly, creating tiny variations in timing, subtle shifts that reveal an unseen companion far away. Now, from that precise ticking, we'll move to a gentler visual idea, one that feels like the universe offering help to our telescopes. Light from distant stars and galaxies can bend around massive objects. In Einstein's view of gravity, mass curves space-time, and light follows those curves. So when light travels past something very massive, like a galaxy cluster, or a dense galaxy, or even a black hole, its path can bend. This is called gravitational lensing, because the massive object acts like a lens in space. It can magnify distant galaxies that would otherwise be too faint to see, bringing the far universe a little closer to our instruments. Sometimes the effect is subtle, a slight distortion, a faint stretching. Other times it's dramatic. Background galaxies can appear as long arcs of light, or split into multiple images, like reflections in a curved mirror. Gravitational lensing also helps scientists map dark matter. Because dark matter doesn't shine, we can't observe it directly, but it still has gravity, and gravity still bends light. By measuring lensing carefully, astronomers can infer where hidden mass must be. It's a quiet reminder that space is not an empty, flat stage. It's a shaped landscape, and light moves through it like a slow river guided by invisible hills. Now, let's return home again back to the sun and place it gently in its true scale. Our sun is only one among hundreds of billions of stars in the Milky Way. From Earth, the sun feels special, and for us, it is. It warms our days, grows our forests, and makes oceans possible. But in the broader census of the galaxy, the sun is fairly ordinary, a G-type main sequence star, one of many. Estimates suggest the Milky Way contains somewhere around 200 to 400 billion stars. Some are larger and hotter, burning bright and short. Others are smaller and cooler, living for astonishing lengths of time. Many likely have planets. Some may have systems very different from ours. When you look up at night and see a scattering of stars, you're only seeing a tiny portion of that vast stellar city. Most of the Milky Way stars are too faint, too distant, or hidden behind dust for the naked eye to notice. And with so many stars, even if only a small fraction have worlds in the right conditions for life, the number of potentially habitable planets could still be enormous. Millions of chances, scattered through the spiral arms. You don't need to turn that into a question that keeps you awake. You can let it become a soft kind of comfort. Life here is not isolated in meaning. The galaxy is large enough for many stories. Now, for a mystery that feels like a candle quietly going out. Astronomers have found cases where a star appears in old records, old photographic plates, and then seems to be missing in modern observations. It's as if a point of light once recorded on film has faded or vanished. In many cases, there are practical explanations. Instruments differed. Data can be imperfect. A star might have been misidentified, or blended with another light source, or obscured by dust. Some stars can dim or change dramatically over time, and sometimes a powerful event, like a supernova, could have been missed when no one was watching at the right moment. But a few cases remain puzzling enough to keep scientists curious. Could some stars collapse directly into black holes with little visible explosion? A failed supernova? Could there be rare transient events that we still don't fully recognize? These vanishing stars remind us that the universe still holds surprises, and that our understanding, though vast, remains incomplete. In a gentle bedtime story, that incompleteness can feel peaceful. Not everything needs to be solved tonight. And finally, we return to a theme we touched earlier: the slow, graceful way galaxies become one. Galaxies can merge. When galaxies meet, it's rarely star-on-star impact, because the spaces between stars are immense. Instead, gravity shapes the encounter. The galaxies stretch each other into streams. Gas clouds compress. New bursts of star formation can ignite, like fresh sparks in the wake of the slow collision. Over hundreds of millions of years, the two systems settle into a single, larger galaxy. Old stars are redistributed. New stars may be born. The overall shape changes, but the material remains recycled into a new arrangement. The Milky Way has merged with smaller galaxies in the past, and one day it will merge with Andromeda, continuing the same cosmic pattern. These unions help build structure in the universe, stitching together larger galaxies within the great cosmic web. And as you listen to this calming narration, you can let that thought become very soft. Even the biggest changes in the universe often happen slowly, quietly, over long stretches of time that feel almost like a lullaby. We're still drifting through this calm, starry bedtime story, and everything is moving slowly, like a quiet breath. If you've been following every word, you can soften that now. Let the phrases become a gentle background. This is a relaxing nighttime story, and you're allowed to simply rest while the universe quietly unfolds. Let's begin with one of the strangest, most soothing ideas in modern cosmology. Sometimes distance changes, even when nothing is traveling the way we usually imagine. Space can stretch and shrink without objects needing to move through it. In general relativity, space isn't a rigid emptiness. It's flexible. It can curve, warp, expand, and contract. Right after the Big Bang, during a period scientists call cosmic inflation, space itself expanded extremely rapidly, so rapidly that distant regions were carried apart faster than light could cross between them. That doesn't break the rule about moving through space faster than light, because the expansion is about the space between things growing. And even today, the universe continues to expand. On the largest scales, the distances between many galaxies are slowly increasing, as if the cosmos is gently stretching its own fabric. But on smaller scales, the opposite tendency appears. Gravity gathers matter. It draws galaxies toward one another, binding them into groups and clusters. In that sense, space can shrink locally as structures form and hold together. So two galaxies can become farther apart without either one firing engines or pushing through space. The space between them simply becomes larger. It's counterintuitive, yes, but also calming, because it suggests the universe is not only filled with motion, it is filled with quiet, changing geometry. Now, keeping that gentle feeling, let's talk about something you can see with your own eyes. No telescope required if the night is dark enough. The Andromeda Galaxy is already visible to the naked eye. On a clear night, far from city lights, you can look toward the constellation Andromeda and see a faint, elongated smudge. It doesn't sparkle sharply like a star. It looks more like a soft brushstroke on black velvet. That small blur is Andromeda, more than 2 million light years away, often described as the most distant object most people can see without binoculars or a telescope. And what you're seeing is not a single point. It's the blended glow of an entire galaxy, an island universe filled with an unimaginable number of stars shining together across a distance so large it almost feels like a dream. In photographs, Andromeda becomes detailed: spiral arms, dark dust lanes, a bright core, and small companion galaxies nearby. But even as a faint smudge, it carries a quiet, emotional weight. It reminds you that the night sky is deeper than it seems. Beyond our own Milky Way, other galaxies are out there, steady and real. And as we mentioned earlier in this sleep story, Andromeda is also slowly approaching the Milky Way, drawn in by gravity for a merger billions of years from now. Even that future event can feel gentle, because it's so slow, so patient, so far away. Now, let's drift toward Jupiter again, not for its storms this time, but for something invisible and powerful. Jupiter's magnetic field is enormous, stronger than any other planets in our solar system. It's generated deep inside Jupiter, where hydrogen is compressed into a metallic, electrically conducting form. As the planet rotates quickly, that moving conductive interior creates a vast magnetic field, so large it extends millions of kilometers into space. Within that field are intense radiation belts filled with high-energy particles. They can be hazardous to spacecraft, and their one-reason missions to Jupiter must be designed with careful shielding and planning. If you imagine, purely as a thought experiment, bringing delicate electronics into that environment, the energetic particles could interfere with them, disrupting operation, causing damage, draining power, and creating problems quickly. In a soft, easy phrase, Jupiter has a planetary-scale force field. You can't see it with your eyes, but it's there, shaping space around the planet, capturing some of Jupiter's moons within its influence, and interacting with the solar wind like a giant, invisible sail. Now, from a predictable magnetic rhythm, let's shift to something that keeps astronomers humble. Stars that don't always behave as neatly as our models would like. Some stars explode with very little warning in the broad outline. Supernovae happen when stars reach certain late stages of life, when internal balance breaks and collapse begins. But in real observations, nature can be less orderly. Some supernovae appear to happen unexpectedly, or after unusual outbursts that hint at instability in the star's outer layers. Sometimes, a companion star can play a role, transferring mass, disturbing the system, or triggering a chain of events that leads to an explosion. In rare cases, a star may even eject material in stages, brightening, dimming, and then erupting again, as if it's shedding layers before the final event. These surprises don't make the universe feel unsafe. They simply remind us that stars are complex. Even the ones we study carefully can hold hidden processes inside, quietly building toward change. And when astronomers observe these events, they refine their understanding of how stars live and die, turning surprise into knowledge over time. Now, let's keep things light and dreamy again, with planets that seem almost unreal in their softness. Some planets are made almost entirely of gas. In our own solar system, Jupiter and Saturn are gas giants, mostly hydrogen and helium, with relatively small cores buried deep inside. But beyond our system, astronomers have found worlds even more extreme. Giant planets with very low densities, so puffed up that they're sometimes compared to floating objects, worlds that would seem almost weightless if you could hold them, which of course you can't. These are sometimes nicknamed superpuff planets. They may have thick atmospheres and small solid cores, and many orbit close to their stars, where heat can inflate their outer layers even more, making them look like enormous, airy spheres. Studying these planets helps scientists understand what kinds of worlds can exist, how atmospheres behave, and how planetary systems evolve. They also remind us that planet doesn't always mean something like Earth in the universe. A planet can be more like a soft globe of gas, glowing faintly, shaped by gravity alone. Now, for a thought so large, it can make the mind relax simply because it can't hold it tightly. The universe may be infinite. Current observations suggest the universe is very close to flat on the largest scales. If it is truly flat, and if that flatness continues beyond what we can observe, the universe might extend without end. If that's true, there could be regions so distant that no light from them will ever reach us. There may be endless galaxies and endless variations of planets and stars. There might even be places with patterns that resemble ours, simply because infinity allows for endless repetition. We cannot confirm infinity directly. Our view is limited by the age of the universe and the speed of light, but the possibility alone stretches the imagination until it stops trying to grasp and starts to simply float. And finally, one of the most comforting truths in astronomy, because it turns looking outward into looking backward. When we look into space, we look into the past. Light travels at about 300,000 km/s, fast yet not instant. Across cosmic distances, even light takes time. So when you see a star, you see it as it was when the light left. When you see a galaxy millions of light years away, you see it millions of years in the past. And when telescopes capture faint galaxies billions of light years away, they're showing us the universe as it was billions of years ago. Young galaxies forming stars rapidly, colliding, changing shape, growing into the kinds of galaxies we see closer to home. In that sense, telescopes are gentle time machines. They let us witness eras long before Earth existed, preserved in traveling light. The farther we look, the closer we come to the universe's earliest chapters, quietly recorded in photons that have crossed immense history just to arrive at our eyes and instruments. And as you lie here, listening to this calming narration, you can let that idea become a soft lullaby. The night sky isn't only distance, it's memory. It's time glowing gently and then fading as you drift toward sleep. We're still moving quietly through this bedtime story, as if we're floating in a dark, warm room while the universe turns outside at a distance. You can let your breathing stay slow. You can let your thoughts be soft. This relaxing story doesn't need effort, only presence, and even that can fade. Let's begin with a simple truth that feels oddly comforting once you let it settle. Space is not completely empty. From far away, the regions between stars and galaxies can look like pure nothingness, perfect black. But the universe doesn't really offer a perfect vacuum. Even in the loneliest intergalactic distances, there are stray atoms, thin traces of particles, and a faint background glow left over from the Big Bang. Closer to home, the space between planets is filled with the solar wind, a steady stream of charged particles flowing outward from the sun, like a quiet breath that never fully stops. And moving through that same space are cosmic rays, high-energy particles launched by distant, energetic events. They cross the solar system and beyond, passing through emptiness that isn't truly empty at all. On the largest scales, galaxies are not sprinkled randomly. They tend to gather along immense filaments, threads of gas, and dark matter, forming what scientists often call the cosmic web. Between those filaments are voids, yes, but even voids contain a thin presence, a whisper of matter, a faint bath of radiation, a subtle environment. So even where you might expect pure nothing, there is still something, and that something influences temperature, chemistry, and motion across the cosmos. In a calming narration, it can feel like this: the universe is never entirely silent. Even its quietest places carry a gentle hum. Now, from that soft, not empty emptiness, let's move to something enormously heavy: gravity gathered into one of the most extreme forms we know. The largest black holes are billions of times more massive than the sun. At the centers of many galaxies, astronomers find evidence for supermassive black holes, objects with masses ranging from millions to billions of suns. And among the giants, one of the most discussed examples is Ton 618, estimated to be on the order of tens of billions of solar masses. A black hole like that is not simply a large object. It's a gravitational anchor so deep that it influences the motion of stars across an entire galaxy. It shapes orbits. It helps organize matter. It can even affect how gas flows and how new stars form, depending on how active it is. These titans likely grew slowly over cosmic time, feeding on gas, swallowing stars, merging with other black holes, and building mass across billions of years. Their event horizons can be vast, so large they would dwarf the scale of our solar system. Yet they remain invisible in the direct sense. We know they're there by watching what happens nearby. Gas falling toward a supermassive black hole can heat up intensely as it spirals inward, glowing in X-rays and other wavelengths. In some galaxies, these bright central regions become active galactic nuclei, powerful beacons visible across enormous distances. Despite the popular image, a black hole isn't a hole like a tunnel. It's a region where gravity becomes so strong that beyond a boundary, the event horizon, light itself, cannot escape. You can let that idea remain distant and quiet, not scary, just profound, a place where the universe shows what gravity can truly do. Now, staying with galaxies, here's a detail that feels like a slow dance step taken the wrong way. Some galaxies rotate in an unexpected direction. Most spiral galaxies spin in the direction set by their formation, the way their original gas cloud rotated as it collapsed. But astronomers have found rare galaxies where parts of the system rotate opposite to what you'd expect. Sometimes the inner disk may rotate one way, while outer regions move another. In other cases, the stars and the gas can disagree, creating a layered motion, one component drifting forward, the other backward, as if two dances overlap. How does that happen? Often through a complicated history, mergers, collisions, or the slow capture of gas flowing in from a different direction. Over cosmic time, galaxies can absorb material like rivers, joining from many angles, and occasionally, that incoming material arrives with opposite angular momentum, setting up a counter-rotating structure. These unusual rotations are clues. They tell astronomers that galaxy growth is not always neat. It can be shaped by chance, by encounters, by long-ago impacts, events so slow from our perspective that they feel almost dreamlike. Now, let's bring the scale down to something intimate, something happening to you right now, so quietly you don't notice it. Cosmic rays pass through your body. Cosmic rays are high-energy particles, often protons, arriving from space. They can be launched by supernovae, by collisions involving neutron stars, and by active galaxies with powerful black holes at their cores. They travel for long distances, sometimes for ages, until they encounter something like Earth. When cosmic rays hit our atmosphere, they create cascades of secondary particles, showers that spread out and continue downward. Many of those particles reach the surface. Some pass through buildings. Some pass through you. Right now, without any sensation at all, a few of these particles are likely moving through your body, harmless in the small doses we experience on the ground, because Earth's atmosphere and magnetic field shield us from the worst of it. Astronauts outside this protective envelope experience cosmic rays more strongly. Some have even reported seeing brief flashes of light in their vision, tiny moments caused by energetic particles interacting with the eye itself. It's a strange and gentle connection. Your quiet evening on Earth is faintly linked through invisible particles to energetic events far away. The universe touches us softly, even when we're unaware. Now, let's return to an object we've visited before in this sleep story, because it sits at the edge of what our minds can comfortably imagine. Some stars become so dense they almost defy understanding. Neutron stars are the collapsed remnants of massive stars, objects only about 20 kilometers across, yet containing more mass than the Sun. Under that crushing gravity, atoms lose their familiar spacing. Matter becomes a packed sea of neutrons. It leads to that famous comparison again. A teaspoon of neutron star material would weigh billions of tons on Earth. Their gravity is strong enough to bend light. It can slow time compared to faraway regions. And their interiors may contain exotic forms of matter we haven't been able to recreate in any laboratory, states that exist naturally in the universe, but remain mysterious to us. Many neutron stars spin rapidly, and some generate intense magnetic fields that shape their surroundings. They're like boundary markers for physics, places where our current understanding still holds, and places where it starts to blur. In a calming bedtime story, you can let that blur be soothing. You don't have to resolve it. You can simply float near the idea, then drift away. And to end this part, we'll visit one of the brightest endings and one of the most important beginnings. A single supernova can outshine an entire galaxy. When a massive star dies in a supernova, it can release an extraordinary amount of energy in a short time. For weeks, sometimes longer, the light from that one explosion can rival or even exceed the combined starlight of billions of stars in its host galaxy. These explosions can be seen across huge distances. Astronomers use certain types of supernovae as tools for measuring the expansion of the universe, because their brightness follows patterns that can be calibrated. But supernovae also do something deeper. They reshape the future. Their shock waves move outward through nearby space, compressing gas clouds and sometimes triggering new star formation, like a gentle push that helps a new generation begin. And they forge and scatter heavy elements. The iron in blood, the calcium in bone, the gold in jewelry. Many such elements were formed in stars and spread by stellar deaths. Without supernovae, rocky planets would be poorer in the raw materials needed for complex chemistry and life. In that way, a supernova is both an ending and a beginning, cosmic punctuation that closes one sentence and opens another. And now, as you rest in this calming narration, you can let these ideas become quieter and quieter until they're only a soft sense of scale and distance and the steady rhythm of the universe, gently guiding you toward sleep. We're here together in this calm nighttime story, and everything has slowed into a quieter rhythm now. Imagine the room dark and safe, your breathing steady, and the universe far away, vast enough that it no longer feels busy, only peaceful. In these last moments of our relaxing story, we'll touch a few final wonders, softly, like distant lights seen through a gentle haze. When a massive star reaches the end of its life, its collapse can send a subtle tremor through the universe as the core compresses into something extraordinarily dense, a neutron star, or in some cases, a black hole. Gravity can rearrange space-time so quickly that it creates gravitational waves. They're not waves of sound and not waves of light. They are tiny ripples in the structure of space itself, spreading outward in all directions. If the collapse is perfectly symmetrical, the ripples may be small, but if the collapse is uneven, if the mass shifts and lurches slightly as it falls inward, those ripples can carry a stronger signature, a kind of twist or wobble in the signal. Catching such events as they happen is difficult. They're rare, and the universe is big. But each detection adds another piece to our understanding of how stars die, how extreme matter behaves, and how gravity reveals itself under conditions we can't reproduce on Earth. And even if we never sense those waves with our bodies, it's quietly amazing to know they pass through us anyway, space-time flexing so slightly that only the most sensitive instruments can notice. Now we'll drift closer to home in scale, to something smaller and surprisingly complex. Some asteroids have their own tiny moons. Even small bodies can have companions, little moonlets that orbit them, held by weak but persistent gravity. These miniature systems can remain stable for long periods, or they can be altered by close encounters with planets that tug on their paths. One well-known example is the asteroid Didymos and its small moon Dimorphos. In 2022, NASA's DART mission intentionally impacted Dimorphos to test whether a spacecraft could measurably change an asteroid moon's orbit, part of a broader effort to understand planetary defense. It's a gentle reminder that the solar system is full of relationships, big and small. Gravity makes families at every scale: planets with moons, asteroids with moonlets, and star systems with multiple worlds sharing the same dark. Now, let's return to the beginning of everything, but in a calm, bedtime-friendly way. The Big Bang produced more than matter alone. In the earliest moments, the universe was filled with energy, and from that energy came particles, matter and antimatter together, as well as light. The fundamental forces that shape nature emerged in that early era too, setting the rules that later allowed atoms to form, and later still, stars and galaxies. One of the quiet mysteries is this: matter and antimatter should have been produced in nearly equal amounts. And yet, for reasons still being explored, the universe ended up with a small excess of matter. That tiny imbalance made all the difference. It meant a material universe could remain one with stars, planets, oceans, and living minds. And the early universe left behind a soft relic: the cosmic microwave background. The faint afterglow still spread across space, like a memory that never fully disappears. Now take a slow breath and let the next idea feel like a gentle release. The night sky contains light that began its journey long ago. When you look up at stars, you are not always seeing them as they are right now. You're seeing them as they were when their light left them. For nearby stars, that might be years. For faraway stars and galaxies, it can be thousands, millions, or even billions of years. Some points of light you see may belong to stars that have already changed or ended, while their older light continues traveling through space, still arriving at Earth long after the source has transformed. So the sky becomes a kind of history book written in photons, each glimmer arriving from a different chapter of cosmic time. You don't have to memorize the chapters. You can simply feel the calm of it. The universe is always sending its past forward, softly, patiently. And now, one of the most comforting truths in astronomy, because it connects you to everything we've talked about. Every atom in your body has a cosmic origin. The simplest element, hydrogen, formed in the early universe. But many of the heavier elements, carbon, oxygen, calcium, iron, were forged inside stars. Stars made them through fusion and through the long chemistry of stellar life. And when stars changed or ended, they released those elements into space. That enriched material became new clouds, new stars, new planets. And eventually, on at least one small world, it became living bodies, breathing quietly in the dark. So when people say you are made of stardust, it isn't just poetic, it's literal. The universe is not separate from you. You are one of its gentle continuations, and with that connection in mind, it becomes natural to wonder softly about what else might be out there. Somewhere in the universe, there may be a planet with conditions like Earth, with billions of galaxies and billions of stars within each one. It seems likely that many planets exist where temperatures are mild enough for liquid water, where atmospheres could form, where long stretches of stability might allow complexity to grow. We haven't found a perfect Earth twin yet, but telescopes continue to discover intriguing worlds, some rocky, some in temperate zones, some with hints that make scientists lean in a little closer. Maybe one day we'll detect a sign, something in a planet's atmosphere, or a pattern of light that suggests life. For now, it can remain a peaceful thought. If the universe made life here, it may have made it elsewhere too, quietly, patiently, under other skies. And that brings our gentle journey to its resting place. We've drifted past hot planets and cold nebulae, through galaxies and gravitational waves, across ideas so large they naturally soften the mind. Each space fact has been a small lantern in the dark, never demanding, only offering a little wonder. If some of these thoughts stayed with you, that's fine. And if they've already begun to slip away, that's fine too. That's the gift of a bedtime story. You don't need to hold every detail. The universe will still be there tomorrow, quietly waiting while you rest. And now, if your eyes feel heavy, you can let them stay closed. Let the muscles in your face relax. Let your breathing slow down, one gentle breath at a time. You can return to this sleep story, this calming narration, on Sleepy Story Facts. Any night, you want something peaceful to listen to while you fall asleep. For now, there's nothing else you need to do. Just drift and rest, and sink gently into deep sleep. As the words grow quieter, and the space between them grows wide, and everything fades into stillness,